I, sixth hour.
Fifth and sixth hour.
Hi guys. Oh my gosh, happy birthday. Yeah, happy birthday, Divya.
Whose birthday?
Divya Surratt.
Wait.
Divya. Happy birthday. I'm not going to be here for it.
Hi, Emily.
Birthday present.
That's, yeah. That's why we'll celebrate that. Okay, so we're talking equilibrium today. We're going to talk lots about the K value, equilibrium constant. Turns out that there's two different ways to calculate a K. But we'll just get to some basics of equilibrium first. We have the definition of equilibrium. There's two different ways that we can define equilibrium. Either way, though, it's the point at which the reaction stops. There's still reactants that can react. There's products that have been made, but nothing is happening. And that's because the rate of the forward reaction equals the rate of the reverse reaction, so the whole thing doesn't have any net change. So yeah, the second bullet point is the point of the reaction which delta G equals 0. If we can take ourselves back a few weeks, we had, oh nuts, this is not calibrated. Delta G equals delta G naught plus RT ln of Q. This term right here is 0, so therefore we can find the Q becomes K when the reaction's in equilibrium. If this term is 0, we're going to rename Q as K. And so we have out of this reaction, delta G naught equals negative RT times ln of K. We're not going to leave this equation. We'll need to use this sometimes in this chapter as well. I warned you about delta G. We'll see a lot of delta G's over the next few months. Oops.
Can you remind us what delta G is?
Yeah, delta G. Remember, delta G is negative. That means the reaction is spontaneous. And if delta G is positive, it's not spontaneous.
Can you go back to delta G negative equals
Okay, thank you.
You may remember this. We just touched on this in chapter 17 when we were doing thermodynamics. I never gave you the name of it. This is called the law of mass action. A couple of Norwegian chemists came up with this a long time ago, 150 years ago. If you have a reaction in equilibrium, this is just a generic equation, but the K value is always the product concentration divided by the reactant concentration. If there's a coefficient in front of a term, that coefficient gets raised to the power. Even if the units don't cancel out, if you don't have the same powers of molarity on top and on the bottom, K doesn't ever get a unit. Remember that. K will always be unitless. It's a ratio. It's a ratio of product concentration and reaction concentration. Or pressures. You can have pressure of products over pressure reactants. Never give a unit to K. So we don't ever analyze the units and say, oh, well, you know, they don't cancel out, so you got polarity squared or whatever. We had to do that for the lowercase k in the last chapter with the rate constant. Capital K, the equilibrium constant, doesn't get a unit. I'm using a subscript EQ here. I don't think we saw the EQ the last time we visited with K. The EQ just means equilibrium. It's a general expression for the equilibrium constant. We'll see that we're going to have several different Ks as we go through the next. I warned you, remember, there's 4 equilibrium units, four chapters. This is one big unit with 4 chapters in it. We'll have KW. You might remember KW is the equilibrium constant for water. Ka for an acid, Kb for a base. Kf for some things. There's KSPs. There's a lot of Ks. They're all found the same way, though. They're always products over reactants. Okay. So this I want to remind you of. I've just barely touched on this in the chapter 17. This part down here. Now we did see that the value on K, if K is greater than 1, that means the reaction makes more products than it has reactants left over. If K is less than 1, that means it ends with more reactants. So the value of K tells us how far the reaction has gone before it hits equilibrium. So the only thing that will affect a K value for a reaction, the equilibrium constant, is the temperature. If you change the temperature, the K will change. And the K changes according to this equation. I know this is ugly, but this is similar to the K expression that we had, the relationship between the rate constant K with temperature. Remember we plotted in the last chapter on kinetics the inverse of temperature versus the natural log of the rate constant K. With equilibrium constant K, we have the same kind of thing, but there's 2 different possibilities. There are, or there is, a possible graph that has a negative slope and a possible graph that has a positive slope. And that's because the delta H for a reaction can be positive or negative. Now in the last chapter that we did on rate constant, the slope of the line was not the equilibrium, the activation energy over R. The activation energy is always positive, so we always had a downward slope. There's actually negative EA over R. But now, since the slope is negative delta H over R, the value of the slope can be positive or negative because the delta H can be positive or negative. So this would be, if the slope is negative delta H over R and it's a negative slope, that means the delta H must be positive. This is an endothermic reaction. And this would be a negative delta H, an exothermic reaction. We're going to deal more with this, and I'm going to give you more depth. I'm just trying to bring some of this back so we can remember, oh yeah, there is a linear relationship between temperature and K. It looks like that.
Is that an E?
That? Yeah. Slope. Yeah, slope equals. Yeah. Okay, So yeah, we're going to get back to some of that when we talk about Le Chatelier's principle and how changing the temperature will affect the K and what direction the reaction is going to shift. I'll come back to those graphs. That handout that I gave you, we're going to do a number of examples from that thing even today. If you look at number 16 in the handout, it's on the back page. Given the values for the standard free energies of formation, tabulated below, loosely tabulated, calculate the equilibrium constant KEQ. Look at the font on that too. This is done with an old-fashioned typewriter. I mean, this question is probably from the 60s. I like it though. It's still good. It's meaningful. Maybe the Zoom dolls were like in undergrad school at that time. They might have been. Maybe they did this problem. Wouldn't that be cool? All right. So we have the reaction. It's a synthesis reaction. Hydrogen plus CO yields CH3OH, methanol. So you have the delta G of formation values. The question is, what is the K value? What do we have to do in this problem? I think we're going to have to use this equation. And solve for K. That's what it's asking us to do. We're going to be able to find delta G naught from the given delta G of formation values. We know R and we know T because it says at 298. So we'll solve for the K. That's pretty easy. We've done enough, hopefully, even if you have not done logs yet. But Algebra 2, you are doing logs currently, yes?
No.
You haven't touched them yet in Algebra? Okay, all right, I was thinking you had hit that. Okay, so anyway, yeah, when you have ln of a value, get the ln of k on one side with everything else on the other side, and then raise both sides to the power of 2. So we can go ahead and do that. ln of k equals delta G over negative RT, and just plug the numbers in for this. ln of k equals delta G. We have to find the delta G by taking the products minus the reactants. Notice that they didn't give us the delta G of formation of H2. Did you see that?
Mm-hmm.
Why not? Yeah, because delta G of formation, just like heat of formation, enthalpy of formation, it's 0. For all elements, the delta G of formation is 0. So the delta G of this reaction, all the coefficients are 1s. It's really easy. Just negative 161.9 for the product minus negative 137.3 for the reactant. And that would be what?
24.6.
Negative 24.6. I'll buy that. Everybody good with that? Okay. So that is kilojoules, notice. So it's negative 24.6 kilojoules per mole. I'll put that. Divided by the R. Now we're going to have to change the R to kilojoules. 0.00831 kilojoules per mole Kelvin. Times the temperature, 298 Kelvin. Okay, so this value is going to give us the natural log of K. Don't leave. Yes?
Is it R?
Yes. Oh, yes, it is. So our K is going to wind up positive. Thank you. Good call. Yep.
It's 2.1.
Okay, so do we find just this value or the K itself?
Okay, so.
K itself.
Got the multiple choice answers at A?
I think so, yeah. That's what I
2.1 times 10 to the fourth?
Yeah.
I would say there's 3 answers that are bogus in number 16 that you should not choose. The delta G was negative, yes?
Mm-hmm.
That means the reaction is spontaneous. If the reaction is spontaneous, that means K is going to be greater than 1, always. If the reaction is spontaneous, K is always greater than 1. So that means that B is no good, and E is no good, and C is no good. So the only two legit choices are A and D.
And D.
So I don't know if you can look at,
Even D
it's possible to have a K that's that big.
Yes.
I wouldn't say D is a no-go right off the bat. You have to have a very negative delta G to have a K that big. Okay?
So it's A.
A is right. Anybody have any questions about that? Did you try that and not get it? Charlie? Am I in your way? Sorry. That's a point there. It's kind of hidden in the parentheses.
Let's see.
Notice all the units in this thing canceled out. Anytime we find the natural log or e to a power, that's always unitless.
So, could you theoretically find the units of a value based on finding k because they have to cancel out?
No. Sometimes we're going to find a k and it had a unit, but when we took the log or something, it just went away. Because like when we find pH, pH is negative log of the hydrogen concentration. We're going to take the negative log of molarity, but then it has no unit. As soon as you take the log of it, it just goes unitless. Okay, so we'll move along. Oh yeah, and this one. Now we learned Hess's law. When we talked about Hess's law, we started to manipulate equations. We had a reaction that was written, a chemical equation written, and if we turned it around, the delta H just changed signs. If it was positive the way it was written, then you turn it around and it makes it negative the same value. With K, we can manipulate the equations just like we did with delta H. However, something different happens to K than what happened to delta H. So by this rule that we call the law of mass action, when we have a reaction that's at equilibrium, the K would be the products, darn it, C times D over A times B. Like that. Products over reactants. Abby?
So let's say K1.
It is K1, yes, because
Okay.
I'm going to do something to it.
Alright, thank you.
Yeah, you'll see what I'm going to do to it. Okay, so let's go ahead and manipulate this thing. Before, I'm going to just have to take, I hate taking this dead time, but I'm going to have to be writing more on the board, and it would be good to write where the print is coming out. Okay. So yeah, if we have to take the reaction and multiply it through by 2, remember what happened at delta H when we multiplied the equation through by 2? We doubled the delta H. Yep. Do we double the K value here? Well, no.
Square.
It's going to wind up getting squared. Here's why. Because if we have 2C and 2D in the numerator, we wind up with C squared times D squared over A squared times B squared. Which is the same thing as, since we're squaring everything, that would be K1 squared. So with the equilibrium constant, if you run a 2 through that as a multiple through the chemical equation, the K gets squared. It does not double. You don't double K, you square it. going to have to get used to that because our brains now are conditioned. You multiply 2 through, you multiply the that number at the end. But now in this case with K it gets squared. And then if we took this original reactant and we turned it around, now we have C and D in the reactants and A and B in the products.
Okay, so it's the inverse.
We don't take the negative of K like we did for delta H. It'll be the inverse of K. It's the inverse. Yep. So yeah, in this case it will be A times B over C times D, which is directly the inverse of K1, so I would just say 1 over K1. Yes?
So if it was 2C plus 2D, equilibrium 2A plus 2D, then it would be 1 over K1 squared.
Exactly. Yep. Yep. Now I've got a couple of examples of that. Just manipulating the equation on the handout. Let's get to that. All right. Flip over to the front page, number 2. Number 2 is pretty simple. So if we're given those 2 given equations, this looks a lot like Hess's law. You're given 2 equations, then we have a target equation. It's pretty simple to see that we'll add the 2 equations together.
Mm-hmm.
I'm going to talk about when we add equations together, though. Let's take a look. So K1 would be, for that first equation, the concentration of C over the concentration of A times B squared. K2, for the second equation, would be D times E over the concentration of C. Then we have Kc, and we can write out what Kc is. Kc is the products over the reactants as well. D times E over A times B squared. But that's not one of the choices. Your choices are in terms of K1 and K2. So what did we do with K1 and K2 to get Kc? What do? You multiply them. Yeah, if we multiply that times that, the C term is going to cancel out, and we'll just get that. So this, I guess, we can add to what we had on the previous page. Anytime you have 2 equations that you add together, you multiply their K values to get the overall equilibrium constant. So it's K1 times K2. And on the multiple choice, it would be D. Anybody have any questions about that? It's pretty easy. Let's go to number 3. Am I doing something wrong?
No. You're great.
Thanks.
Good.
Good. Okay, so for number 3 now, this is going to look like things that we've done before. We're going to have to manipulate. I'm going to give you a moment and see if you can, based on what we've learned now, manipulate those 2 given equations to get the target equation, and then what do you do with the K's? I want you to try to not use a calculator for this one. At all. Don't be afraid. Okay, how are you doing on this one? Could you do it without a calculator? Yes? We need to turn the top one around, and then both of them need to get divided by 2 so we can get the target equation. So that was what I was doing here. I'm dividing by 2 for both. So that means the k's, I need to take the square root of the k. Not divide by 2, take the square root of it.
So it'll be 8 over 15.
Yeah, so now we add these two together, and we multiply the k's. So we have the square root of 64 times the square root of 1 over 225. And those are nice because they're both perfect squares. That's why I'm asking you not to use a calculator. You should be able to figure that out. So you wind up with 8 over 15. And can we evaluate 8 over 15 without a calculator? Well, look at your answer choices. There's one answer choice that's good. 8 over 15 is just over a half, right? 8 over 16 would be a half, and 15 is 1 less than 16. So, yeah, 0.53 is what we would come up with. Sorry. Any questions about that? It's not bad. Looks like Hess's law. We just have to make sure that we know if we're dealing with delta H, we do one thing. If we're dealing with K's, we have to multiply and take kind of a multiplicative relationship rather than an additive relationship like we do with Hess's. All right, so the next thing, and this will be the last thing I think for today. There's two different ways we can find the K, depending on what we're given. If we're given concentrations, then the ratio of the concentrations at equilibrium is called Kc. But if we have a gas phase reaction and we have pressures, then the equilibrium constant that we'll find is Kp. They both are products over reactants. And there is a relationship between the two. We can go from a Kc to a Kp for gases. I want to show you how we do that. Kc is the ratio of the concentrations of products over reactants. P is the ratio of the pressures. And what I want to show you here is how we can go between Kc and Kp. If you have Kc, how do you find Kp, or the other way around?
You said C was the ratio of
The concentrations, yeah. And then P is the ratio of the pressures. So we're going to use this equilibrium reaction and find the Ks two different ways. Kc. Now, if you're given a K value, if it just says K and it doesn't specify which K it is, assume that it's Kc. Just like in the last chapter, when the problem said find the rate law, they meant the differential rate law, not the integrated. If they wanted the integrated, they would tell you find the integrated rate law. The same kind of thing here. If it just says K, then it means Kc. So yeah, the Kc of this reaction will be the products over the reactants. I chose this reaction because it does have coefficients in the term, so we're going to have the exponents. I want to derive how we go from Kc to Kp. So we'll just establish first that Kc is the ratio of the concentrations, Kp is the ratio of the pressures. Are the two the same thing? No, they're not. You don't get the same numerical value for both. You all good with that? Is there still one? No matter which expression we use, either KC or KP, there's no unit. Okay, so here's what we're going to do if we know one of them, how to find the other one. So we're going to start with the ideal gas law. That's a good place to start. PV equals nRT. If I divide the volumes out from both sides, that divided by V and that divided by V, nRT over V is the same thing as N over V times RT. We've talked about this before. It doesn't matter what order you do multiplication and division in. It'll give you the same thing. So the pressure of any gas is equal to N over V times RT. Now what is N over V? What do the units give you? It's molarity. You can have a molarity of a gas, not even dissolved in water. Moles over liters. And in the ideal gas law, the V has to be given in liters. So this is moles per liter, so this gives us the molarity of a gas. How many moles of a gas are crammed into a liter? I have that there. So yeah, if we were to solve for that term, so pressure is equal to the molarity of a gas times RT, and therefore molarity would be pressure over RT. So if this, it gives us the molarity of a gas, then, am I good to change it? When we have the expression for Kc, and remember, I'll rewrite the chemical equation. We have N2 plus 3 H2s yields in equilibrium 2 NH3s. So Kc is the concentration of the products over the concentration of the reactants. This is a gas phase reaction. Nitrogen, hydrogen, and ammonia, when they're pure, are all gases. And remember, from the previous slide, we saw that molarity of a gas equals pressure over RT. So that means this. That means when I have the molarity squared over the molarity of those two reactants, that's the same thing as the pressure of NH3 over RT squared. That whole thing, that's the molarity of the numerator squared. That's divided by the pressure of N2 over RT times the pressure of H2 over RT cubed. So I've just replaced the concentrations with the expression for concentration, pressure over RT. Okay, so we have pressures of the three gases, and then R's and T's are all constants. So let's see if we can make sense of this. We have pressure of NH3 squared in the numerator, pressure of N2 and pressure of H2 cubed in the denominator. So it's going to look like this. I'm going to keep the pressures separate from the RTs. It's going to be pressure of NH3 squared over pressure of N2 times pressure of H2 cubed. And that's just the pressures. And then we have times, what's going on with those RTs? Can we simplify the RTs? This is RT squared in the denominator. This is RT and RT cubed in the denominator of the denominator. Where do they belong? In the numerator. Yes. Things that are in the denominator of the denominator go in the numerator. Because we're multiplying the denominator, the reciprocal of the denominator times the numerator. Yes?
Yeah.
Okay, so what do we have? We have RT to what power when we evaluate there? Positive or negative? Positive. It is positive. Yeah, because you have RT squared in the denominator. Really, this is, you got the RT squared from that RT is down there. And this, we have RT to the fourth power up on top, because it was in the bottom of the bottom. So you've got RT to the second power. You okay with that? All right. What do we have right here? What's in the red box? It's KP.
Yeah.
Right, that's our KP. The ratio of the pressures, the products over the reactants. Yes?
Wait, so why couldn't you just set those two equal in the first place?
What two? KC equal to KP?
KC equals to the green stuff. You had the original and then you made it equal.
Yeah, I was saying, okay, the KC is the ratio of the products over reactants. Then I substituted the this expression for molarity in. So I can try to get to a term of pressures. All right, so in the red, let's get rid of this now. I don't want to get rid of it. Oh, don't look at that. We're not done yet. I want to do one more simplification. So this in the red box, I'll just make it red, is our KP. Now my only other thing is, where did this 2 come from? Can we generalize how we got that 2? I know we subtracted exponents, but can you generalize that 2? How did that 2 come about? The number of what? Yes, it was the coefficients, right? But 2, we got 2 by subtracting these 2. What do the 4 and the 2 up there represent? They're the coefficients. And it looks like it was these coefficients minus these coefficients. So would you buy that I could call that Kp times RT raised to what power? It's the negative delta N power. Delta, it means products minus reactants, right? Final minus initial. So this is actually, 4 minus 2 was reactants minus products. That would be the negative of the delta. Yes? Because we took RT to the 4 minus 2. The 4 was in the reactants and the 2 was in the products.
Wouldn't that make the RT in the denominator?
It does make it in the denominator, yeah. Yeah, so it really should be Kp over RT to the n delta N power. You don't like that?
But it's being multiplied for the equation once you're not. It's being multiplied.
To the positive 2. What's delta N up here? No, it's negative 2. It's 2 minus 4. See what I mean? Yeah. So it is, up here, the delta N is negative 2. Everybody see that? Yeah, it is. It is.
Oh, so it's negative of the.
Right.
So
the negative of negative 2.
And so KC and so KP is equal to K.
Yes, and that's where I wanted you to see this, how we got that. Now, normally, we express this thing with a positive exponent. So if this remember is the same thing, I'm going to just squeeze this over here. This is Kp over RT to the delta N. That's hard to read. So that's what the negative delta N means. It means it's in the denominator. So that's all equal to Kc. Cleaning this thing up, normally we write this thing in terms of Kp. So I moved the RT over to the side with Kc. And therefore, the relationship between Kp and Kc goes like this. It's Kp equals Kc times RT to the delta N power. Now this is a positive because I've actually moved this term over to the other side. That's our relationship between Kp and Kc.
And a different R value?
Yes. See my comment down here? For this, the ratio, the Kp should always use the unit atmospheres for your pressures. In fact, Kp is dependent on the pressures only in atmospheres. So if you're given any other pressure unit, you have to change the atmospheres. Do I say that anywhere on here? Have I said that before this? Okay. Yeah, pressure has to be in atmospheres. And therefore, the R value that we're going to have to use is the one that corresponds with atmospheres, 0.0821. Yes?
So why did you just say delta n? How does negative delta?
Oh, that was, so I had Kc equal to Kp times this term. But then I solved it for Kp. So I moved the RT term over to the other side. So it was negative, but when I multiplied by both sides by it, it became positive. So this is correct. The part that's in the squiggly green box is correct. Once again, this is just a flaw of my memory that I have to use a memory trick for this. When I'm under pressure, I can't remember which one is Kp and which one is Kc. So I either have to derive it from the beginning, like I did, which you could do, or give yourself a memory trick. And I think of this, forgive my fairiness, but I call this the Prince Charming equation. To myself, I call it the Prince Charming, meaning that the P and the C, Prince Charming. So I can remember, okay, Kp, the P is going to come first. So I know which to put the P and which to put the C on. So use whatever P and C you want. That's what helps me. I've seen a few Disney movies.
Never once during a test I've thought, oh my god, let me derive this equation.
Well, you
That's
might. You
never
might at
happened
DTS.
to me.
You might. You've got a good memory, so you don't have to worry about that. Well, it's good enough.
Well, it's more work to remember, right?
Not really. That's easy.
In some cases, yes. Yeah. If you have a good memory, then it's not a big deal for you to just remember stuff. I don't. Maybe you do. Maybe you do.
If I do it
Oh, the
enough,
worse they are, the better you remember.
if I do it enough times, I'll remember it.
Yeah.
If I do it too many times, I'm just gonna get bored and then I forget it. Because like I just like, oh, I know how to do this.
Yeah,
And
that happens,
then
yeah.
That's when I make mistakes.
But remember, when you have to come up with memory tricks, make them ridiculous. The more out of ordinary they are, the better you remember them. Okay, would you go with me? Let's just go to number 10. And let's do this one and then we'll quit for today. Number 10. It's probably a bad one to finish with because it's so simple, but we will just stop with this one.
Wait. And also, does K?
What's that, Mary?
Does temperature have to be in Kelvin?
Absolutely, yeah, because you got the R term in it. Yep. All right, can I have your attention, please? Just let's do this last one. Ready? Number 10. Consider this reaction, the hydrogen shift. You got water plus CO yields hydrogen plus CO2. Looks more like an oxygen shift to me, not a hydrogen shift. But the Kc is given to us, is 1.873. The question is, at the same temperature, what is Kp? This is a really easy question. Yes? Mary?
Yeah,
You have to convert to Kelvin.
Yes. When you use the RT, you always have to use Kelvin. Remember, anytime you have just T in an equation, you have to use Kelvin. If it's delta T, that's when you can get away with keeping it in Celsius. All the T terms, though, all of course, are in Kelvin. Joe?
Really?
What's the matter, Joe? How come you give me that look?
It's too easy. Really?
I know. That's why I didn't want to end with this one. It's too easy.
Oh, wait, well, you just said we were, isn't it?
Yes, I did, but I don't want to.
Oh, what?
Well, too bad. What happened?
What makes this one really easy?
Wait,
You
What
That's
is?
when it is 0.
Yeah, your delta n is 0. The power on the RT is 0. So what does that mean? That means Kc equals Kp. Right. Or Kp equals Kc.
That's no
Yeah.
fun.
Because I know. I feel like I shouldn't have said this. Oh, you're like, maybe we'll just stop now so everybody can leave happy.
I'm not gonna lie, if he gave me this question on the test, I'd be like, too easy. And then do something wrong.
We don't want to overthink.
Yeah, I was like calculating like 700.
Right. I
273.
know.
Oh.
You can go ahead and plug it in. The Kc was given 1.8.
Oh my god.
Okay.
Yeah, we do all that work and then we realize, the power on the RT is 0. Yep.
Now I'm so confused.
Okay, we're done.